Hello everyone, I am Siti Zulaikah from Mechanical Engineering Study Program 2019 in Sampoerna University. So here I would like to explain about my senior mechanical laboratory experiment that is conducted in this semester, and it will cover about the fluid mechanics, thermodynamics, and heat transfer. Then, as I have mentioned before, there will be three experiments should be done. So from the fluid mechanics experiment, it will be conducted for the water hammer phenomenon, and for the thermodynamics and heat transfer experiment, it will conducted for the Stirling engine device. And this experiment will be detailed explained later on. First, from the preparation of the experiment that consists of design step, shipping planning, and the purchasing components. And then the second is assembly. The third is experiment that consists of working principle, data collection, and the result expected. And for the fourth is analysis, and then conclusion and the feedback. And first, let's start from the preparation of the experiment for the water hammer phenomenon as Stirling engine device. So in this experiment, I am in group with Armalia Clara and Hanifatu Tagia. Fortunately, we are still in our boarding house in Pancoran, Jakarta. Therefore, the experiment will be conducted by Armalia and I first because we are in the same boarding house. Here I did for the Stirling engine and Armalia with the hot water hammer. Then as the setup is done, it will be sent to Hanifatu Tagia with no shipping cost. As you can see in the map, we just only need to walk around 5 minutes to each other. And here's for the preparation of water hammer phenomenon. First, this is the design step for the water hammer, and we need to prepare the tools such as saw, pliers, cutters, and scissors, and for the components such as pressure gauge, water flow sensor, Arduino Uno, transparent hose, PVC pipe, STD, stop valve, elbow pipe, seal tape, T-thread, pipe glue, brass hose nipple, double nipple, flexible hose clamp, sealing glue, and pipe clamp. And this picture is rough schematic that mainly consists of valve as the water source, water flow sensor, Arduino Uno, pressure gauge, and stop valve. And this is the component of water hammer that is purchased by online and offline, with the total is around 390,000 rupiah. Besides, there is also free component that we don't need to buy such as Arduino Uno, PVC pipe, elbow pipe, and the tools. And then we are going for the preparation of Stirling engine device. And then this is the design step for the Stirling engine, and it will consist of two design because of some reason that will be explained later on. For the first design, we need to prepare the tools such as hammer and nail, saw, screwdriver, pliers, cutter, scissors, and sandpaper. And for the components such as cans, discs, steel wool, elbow PVC, pipe PVC, balance, stainless steel, rubber sheet, rubber band, sealing glue, super glue, coin, powder, pillows, and bottle cap, candle, connector, and thermometer. So the picture here is the rough schematic that, that will be conducted for the Stirling engine device. And then this is the second design of the Stirling engine because we need to redo it. And for the tools and component actually is still the same. However, for the hammer and saw, we don't use it as the tools, and for the component, we also don't use pipe PVC, powder, pillows cap, connector, and we also add the baking soda. And here's the raw schematic of the Stirling engine as the second design. So this is the component for the Stirling engine that is purchased by online and offline. Same with the water hammer before, with the total is around 139,000 rupiah. Besides, there is also free component that we don't need to pay it, such as cans, candle, super glue, duct tape or masking tape, pen tube, rubber sheet, rubber band, baking soda, small stainless steel wire, butter and pillows cup, lighter, and tools. Then here we are going for the assembly process of the water hammer phenomenon and Stirling engine device. First, this is the assembly of water hammer that Later on will consist of 3 different setups because we need to fix the leakage occur until we don't have the leakage. This is the video of the first setup. So this is the first setup of the water hammer assembly that consists of valve from the water source and then pipe PVC, elbow PVC, pipe PVC, SDD, hose snapper, transparent hose, snapper, SDD, pipe PVC, SDD, water flow meter, cable and Arduino and laptop, and then SDD, pipe PVC, teach rod and pressure gauge, pipe PVC, SDD, hose nipple, transparent hose nipple, SDD, pipe PVC and stop valve. Between the pipe it will use the pipe glue for connecting, and between the hose nipple, transparent hose and rod it will use seal tape for the connecting. And in summary, the STD that is used is 6 and the hose nipple is 4 and the other is 1 and the pipe PVC and transparent hose is used as needed. And this is the second video for the setup of water hammer. So this is the second setup for the water hammer assembly. Actually it is the same with the first setup. However, we change some component because there is a leakage in the first setup. Here we add 2 flexible hoses before and after the flow meter sensor. Therefore, the component that is used in this second setup, there is flexible hose 2, SDD4 and hose nipple 6. And this is the last setup for the water hammer assembly that later on will be used for the analysis because there is no leakage here anymore. And this is the last setup for the water hammer assembly. Here we only change the pipe here before with the transparent hose that directly connect to the valve from the water source. Therefore, the component used in this last setup is reduced to flexible hose for 2 quantity SDD3 and the hose nipple is 5. Then here we going for the assembly of the Stirling engine device. So this is the assembly of the first design of the Stirling engine that consists of 2 cans, 2 coins, elbow pipe, PVC pipe, cap of the pillocks, and the black is the rubber sheet. And here the component will be connected with the glue from the sealant, and there is a hole here between the elbow pipe and the cans. So this is the crankshaft assembly of the Stirling engine. First, this part is for this piston that consists of the connector, and then cap of the can, connector again, steel wool connector again, cap of the can, connector again, and the stainless steel wire. And for this part that will be connected with the cup of the pilox, it consists of the balloon, and bill in the bottom of the balloon there will be cup of the bottle, and the top of the balloon there will be rubber sheet and the cup of the bottle, and this is the stainless steel wire. And for this disc rotation, it will consist of the bottle, cup, and then two discs and one of the coin and the stainless steel wire. And here it will be connected to each other by using connector. Then unfortunately, for the previous assembly of the Stirling engine, this is still doesn't work for the movement of the piston. So we change the stainless steel wire to be straightforward like this, and we change this stainless steel wire to be the smaller one. And we also add the additional cans in the middle of the setup because the piston doesn't work in and doesn't move in when we use two of cans. So we add three, and it will looks higher later on. And for the last setup of the first design, it looks like this. And then this is the assembly of the second design that consists of two cans from the Coca-Cola cans, and then we still use two coins here, and we also use elbow pipe, and there will be hole here, but we don't use such as a pilox cup here. And this is the assembly of the crankshaft for the second design. For this part, for the piston, we use the cup of the cans and then steel wool and then cups of the cans again, and it will be connected with the super glue, and this is the stainless steel wires. And for this part it will use a balloon. For the bottom it will use a rubber sheet, and for the top also use a rubber sheet, and it will be connected with the elbow pad with the rubber band. And here between the rubber sheet and balloon, it will connect it with the super glue. And here for the disc rotation, it use the bottle cap and then the rubber sheet, and then two discs and then the rubber sheet again and the stainless steel wire, and it will be connected as like the first assembly. And here this is use a larger stainless steel wire in the bottom because there is a mistake before and the piston still doesn't move, so we change for the upper with the smaller stainless steel wire, and for this it is also using a smaller stainless steel wire. Then here we going for the experiment of the water hammer phenomenon and the Stirling engine device that we have assembled before. First, this is for the experiment of the water hammer phenomenon. Then the working principle of the water hammer is water hammer will occur when the open valve suddenly closes, and then the water slams into it, and when the pump suddenly shuts down, the flow reverses direction back to the pump. And since water is incompressible, the impact of the water results in the shock wave that propagates at the speed of sound between the valve and the next elbow in the piping system or within the column of water after the pump. And here is the illustration of the water hammer when the open valve is suddenly closed. And from this experiment, the result expected is after the high pressure generated by the pressure gauge and flow rates generated by the flow meter sensor from the experiment, it will compare with the theoretical result from the Jauski equation. And then this is the pressure that is generated from the pressure gauge from the first experiment or for the first assembly setup before, during, and after. And then this graph shows the flow rate generated from the flow meter sensor with the circle rate indicated with the water hammer occur, and from this flow rate and the pressure value it is summarized with this table before, during, after the phenomenon, with the pressure before the water hammer is 0, during the water hammer is 8, and after the water hammer is 0 psi. And for the flow rate, before is 525 liter per hour, and then during water hammer is 250 liter per hour, and after the water hammer is 525 liter per hour. So this is the pressure generated from the pressure gauge in the experiment 2 or setup 2 before, during, and after the water hammer. However, unfortunately, in this experiment 2, the water flow rate cannot generated because there is a mistake in the connecting the cable between the flow meter sensor and the Arduino Uno. Therefore, the table here only summarizes the pressure before, during, and after the phenomenon. Before the water hammer, the pressure is 0 psi, and during the water hammer, the pressure is 12 psi, and just a moment reduced to 10 psi, and after the water hammer is 0 psi again. Lastly, this is the pressure generated from the pressure gauge from the experiment 3 or setup 3 before, during, and after the water hammer. Then again, the graph here shows the flow rate of the water with the red line or red circle indicate for the water hammer occur, and for the pressure and water flow rate is summarized in this table before, during, and after the phenomenon. Before the water hammer, the pressure is 0 psi and the flow rate is 400 liter per hour, and during the water hammer, the pressure is 20.5 psi and later on reduced to 14 psi, and the flow rate is first 0 and then increased to 440 liter per hour, and after the water hammer, the pressure is 0 psi and the flow rate is 400 liter per hour. Then here we are going for the experiment of the Stirling engine device. So the working principle of the Stirling engine is an engine that transfers the flow of heat into mechanical work such as spinning a crankshaft. Here the flow of heat means that there must be two reservoirs that are separated, and this reservoir must be at a different temperature in order for this flow to take place between them. Then the Stirling engine needs a hot section and cold section that are insulated from each other to produce mechanical work, and this heat transfer from the hot section to the engine. Some of the energy leave the engine as a useful mechanical work, and some of it leave as a heat transfer to the cold section, as shown in the illustration in the right picture. And the Stirling engine also can be categorized as an external combustion engine, like or similar as a piston. And here also the illustration should be the Stirling engine work. And then from this experiment, the results expected are it should generate temperature or heat difference as a heat transfer experiment, and then from this temperature or heat difference it will generate a work or mechanical work as a thermodynamic experiment. This mechanical work indicated by spinning of the disc in Stirling engine. Then as there will be two design assembled in the previous steps, so this is the design 1 and design 2 of Stirling engine. Then after some experiment for both of the design 1 and design 2 of Stirling engine, It shows that Stirling engine still doesn't show any self-rotation when it is being heated above the candle for both of the design. Therefore, in the end, it only calculates the temperature for design 1 and design 2. However, for design 2, it will be 3 cases generated. For design 1 here, the initial temperature for the hot and cold is 31.8 degrees Celsius, and the temperature after heating after 5 minutes, the hot temperature is more than 110 degrees Celsius, and the cold temperature is 48.3 degrees Celsius. And for the design 2 with the case 1, the initial temperature is 32.9 degrees Celsius, and the temperature after heating after 2.5 minutes with the hot is more than 110 degrees Celsius, and the cold is 44 degrees Celsius. Then, for the data of design 2 and case 2, the initial temperature is 30.3 degrees Celsius, and the temperature after heating after 2 minutes for the hot temperature is more than 110 degrees Celsius, and the cold temperature is 46 degrees Celsius. And for the design 2 with case 3, the initial temperature is same with the case 2, which is 30.3 degrees Celsius, and the temperature after heating after 2.5 minutes, the hot temperature is 110 degrees Celsius, and the cold temperature is 39 degrees Celsius. And here we are going for the analysis of the water hammer phenomenon and the Stirling engine device. First, this is analysis for the water hammer phenomenon. In this analysis of the water hammer, the data from the experiment such as the pressure and the flow rate, it will compare with these Joyce equations, these two equations, that later on the change in pressure is one that will be compared with the experiment data from the water hammer that have been done before. And then this is the calculation from the Joyce equation from the theoretical data with the bulk modulus or K over the water is 2.90 times 10 to the power of 9 Pascal with the assumption no air bubbles on the water. This is taken from the source in the internet, and then some of the data also taken from the pipe or T-graph of the pipe and the source in the internet, and the Q is taken from the flow rate from the data of experiment 3, and after this is calculated by the Joyce equation, the change in pressure for the theoretical data it generated for 6.53 psi. So after comparison between the theoretical data or Joyce equation with the change in pressure is obtained to be 6.53 psi with the experiment 3 that the data is taken from during the water hammer, and the change in pressure is obtained to be 6.5 psi, and after it is compared to each other, it shows that the result is almost the same, only different in the commas. So it can be said that the Joyce equation can be used to calculate the change in pressure for the water hammer. So this is the problem or leakage for the experiment or setup 1 during the water hammer. Therefore, the pressure generated from the pressure gauge is very small. And then this is the problem, again the leakage for the experiment or setup 2 of the water hammer. Even in this setup, the leakage in the pressure gauge is reduced, but the leakage is moving to the valve from the water source. As you can see, this is the leakage from the valve And then this is the leakage during the water hammer in the pressure pipe. And this is the leakage during the water hammer in the valve. It's very big leakage in here when the water hammer is conducted. And then this is the analysis of the Stirling engine device. So in the analysis of the Stirling engine, as we know that the Stirling engine we made didn't work as desired, so the problem might come from several reasons, and it will be explained here. And the problem, first, it expected come from the wrong direction or wrong design from the part here and part here. The crankshaft here should be going up when meanwhile the part of the chamber here should be going down. But for the design one, it shows the reverse of the direction. Then for the design 2, it have shown the correct direction, but we still don't know whether this direction is correct or not. And as we can see, this is the design 2 for the crankshaft direction. And this is the manual rotation for the design 2. And then in summarize, this is the crankshaft design of the design 1 of the Stirling engine, and this is the crankshaft of the design 2 of the Stirling engine. As we can see in the design 1, the direction of the crankshaft is wrong because the stainless steel wire is strike forward, therefore it cannot generate going up and going down movement. However, in the design 2, there is a 90-degree part of the stainless steel wire in this part and this part. Therefore, for the design 2, it can generate going up and going down movement for the part that should be going up and going down. Besides, the problem also might come from the proportional dimension of the Stirling engine. When the dimension between the hot reservoir air and cold reservoir before and after the elbow pipe is not proportional, it can affect the hot flow or cold flow later on. And then it also can affect the crankshaft design because the crankshaft design it will depend on the cans or the dimension of the hot and cold reservoir air. So it might be generate some problem if the dimension before and after the elbow pipe is not proportional. Same with the design 1 of Stirling engine. Design 2 also make me generate a problem same with the design 1 such as proportional dimension for the hot reservoir and cold reservoir. Therefore, it is important to know what is the right dimension of the hot reservoir and cold reservoir because it can affect later on between the crankshaft or the flow of the heat later on. And then the next problem is the leakage in the elbow. From the design 1 of the Stirling engine, as we can see that the between the elbow pipe and the cans is connected or joined with the sealant glue, it might that the leakage occur here. Indeed, when the Stirling engine is heated above the candle, and then as this is also a hole to connect the stainless steel wire and the balance, so it might be that the leakage also occur here. And for the design too, for the Stirling engine, even between the elbow pipe and the case use superglue and baking soda that generate a strong connection, but it might be still a leakage here, and the part between the balun and the stainless steel wire here also might generate a leakage because it's not tied well. Therefore, because of this leakage, it might generate the or make the steel engine didn't work. And then the leakage also might be come from the middle of the can. As you can see in the design one, the leakage is very big that it can generate pressure from the below can coming out. And for the design one, it have anticipated with the tube pen, but it cannot ensure that the leakage is not here because there is still a small hole here between the stainless steel wire and the pen tube, but I think the leakage is reduced here. The next problem might become from the pressure and temperature difference of the steam engine, as it is stated that a higher pressure and higher temperature can generate more effective and powerful steam engine. However, as we know that the leakage from the previous explanation from the middle of the can and the elbow pipe, it already reduced the pressure. Then, from the temperature that obtained from the experiment, it showed that the temperature difference also relatively small. However, as it is shown, the temperature difference is increasing for the different treatment between Stirling engine 1 and Stirling engine 2. For the design 1 and design 2, with the case 1 of the Stirling engine is directly put in the above of the candle. Meanwhile, design 2 with the case 2 and case 3 is added with the water so that the cold temperature is decreased. However, in design 2 with the case 3, it is also added with the insulation heat from the other can, or it can be said that the steel engine not put directly above the candle. And then compare with the design 1 and design 2, design 1 also have a bigger reservoir rather than design 2. Therefore, by this data, it can be said that to generate higher temperature difference, it might be done by having insulation heat from the candle so that the hot reservoir heated faster, and then added some water or ice in the second can so that the temperature of the cold reservoir not increase faster, and the steam engine also have the small reservoir. And then for the conclusion, with the water hammer worked after several revisions and experiments, and when it is compared between the experiment and theoretical data, it shows that the value is likely almost the same. However, the possibility of the error may be still appear here. And for the recommendation in the next experiment, it should be understand the basic concept of the water hammer phenomenon itself, and then prepare the component needed and ensure it is fit to each other, and then pay attention on the assembly and the leakage of the water hammer assembly. And for the steering engine, still doesn't work due to many possible errors, and maybe it also lack of the understanding of the mechanism of steering engine itself. So for the recommendation of the steering engine device, we should understand the basic concept of the steering engine device first, and then prepare all the concept well, and then we also should consider the tools and the component that will be needed, and then the design and the dimension of the steering engine, and then the leakage of the steering engine when it is assembled. And then for the feedback of this experiment or activity, actually the activity is fun because we try to build self-experiment or our hands-on experiment, and then it directly introduced for me some tools or components name, but sometimes it is also difficult to find the tools or component needed, so it might be generate or feel lots of feelings because sometimes it is disappointed or tired to for the failed experiment, but it teaches me a lot, and I hope I can be better in the next for the next experiment or other experiment. I think that's all from me, and thank you.